So we are discussing about top-down parsers, isn't it? What exactly is top-down parsing? Top-down parsing can be viewed as an attempt to get the leftmost derivation of the input stream. So while constructing the parse tree, actually we use leftmost derivation. So we start with the start symbol at every step. A non-terminal is replaced by the right hand side of the rule. So in top-down parsers, we have seen different classifications. A top-down parsers can broadly be classified into how many categories? Two categories broadly. One is with full backtracking. The other one is without backtracking. Under the with full backtracking, we have a best example, brute force technique. Whereas in without backtracking, actually these parsers are even called predictive parsers. We have predictive parsers wherein there are two types. One is recursive descent and the other one is non-recursive descent. Or it is called ll1. So if you look at with the full backtracking, in the brute force technique, what is the problem? Generally in the design of any top-down parser, the main problem in the design is what? If a non-terminal has more than one alternative production, the parser should have a mechanism to decide when to use this one, when to use this one, or when to use this one. So this particular problem is handled by different parsers in different ways. For example, if you look at brute force technique, the main this problem is resolved by what? Whenever a non-terminal has to be expanded, always first time first alternative only. Whenever it is the first time first alternative. So because of this, what is happening? Lot of backtracking is involved. That's why these parsers are dead slow. Hence, practically these parsers are not being used. And if you look at the other category, these parsers are actually called predictive parsers. Why the name predictive parsers? Because they are capable of predicting the right choice for at any point of time for expanding a non-terminal. In order to construct any predictive parser, remember there is a restriction on the grammar. Given a grammar has to be free of left recursion and should be left factored. Under this we have two types, recursive descent and non-recursive descent, that is called ll1 parser. What is recursive descent? Recursive descent is nothing but writing recursive procedures for every non-terminal. Grammar is nothing but set of rules for every non-terminal. The way you choose different alternative productions for a non-terminal, that if you write as a procedure, then it becomes recursive descent parser. Remember here recursive descent parser actually I have given under this predictive parser category. But in some textbooks, you may find recursive descent parser under some other category. It can be non-predictive also. In the sense, remember in the predictive, non-predictive, mainly difference is what? Predictive means it is grammar is left factored and is free of left recursion. Given a grammar, you can even construct a recursive descent parser without left factoring or even without eliminating the left recursion. You know what is the advantage of going for eliminating the left recursion or even left factoring. Left recursion always may lead to infinite loop for the parser. That is the reason we prefer eliminating the left recursion. And left factoring always helps avoiding backtracking, because backtracking is a costly procedure for in implementation. That's why once you take out that common prefixes that we call left factoring, you can avoid backtracking. So given a grammar, if there is a left recursion, if you don't eliminate the left recursion and write recursive procedures, then you can say it's a non-predictive recursive descent parser. Given a grammar, if you eliminate the left recursion and left factor and then write the procedures, then you can consider that as a predictive parser, recursive descent parser, which is a predictive parser. So don't get confused with non-predictive, predictive. because in some textbooks you may find recursive descent parser under even a non-predictive also. Okay. And the restriction of this is what? If the grammar is so simple, if it contains only less number of rules, you can go with writing the recursive descent parser. But generally, if you look at any high level language, the number of grammar rules may not be so less. Hence, the most widely used parser is the non-recursive descent parser, or we call ll1 parser. So, what exactly ll1 parser does? In ll1 parser, this problem is completely handled by the parsing table. So, given a grammar, the ll1 parser first constructs a parsing table by using first and follow sets. Once it has the parsing table, by using the parsing table, it actually parses the given input string. So, we have seen how to construct, given a grammar, how to construct the ll1 parsing table, and also we have seen what is ll1 grammar. What is ll1 grammar? The traditional definition is, given a grammar, follow the procedure of ll1 parsing table construction, construct the parsing table. In the parsing table, if there are no multiple entries, then you can say the grammar is ll1. Okay, let's just review that procedure once again by taking an example. Let's construct an ll1 parsing table for this particular grammar. So, to construct the ll1 parsing table for a given grammar G, what is the procedure? Look at the grammar. The first step is check whether there is a left recursion. First, eliminate left recursion and left factor the grammar. So, look at this grammar. Can we start with this grammar straight away? No. If you look at here, there is a left recursion. In the first rule, there is no left recursion. Here, there is no left recursion. But in the second rule, there is a left recursion. So, first step is eliminate that left recursion in the rule A. Then what you get? A to D, A, B, A dash. This is beta. So, A, B, A dash to alpha, that is dA dash or epsilon. So, we need to take out this and should use all these rules. So, with these rules, how do we construct the table? For constructing the table, the number of rows are given by non-terminals, columns are given by terminals. So, what are the different non-terminals you have here? S, A dash, B and C. What are the different terminals you have? A, B, D, G, F. In addition to this, one extra terminal, that is dollar. So, now take every rule and place it, find its position in the parsing table, that is parsing table construction. For example, if you take S to A, how do we place this? In the row S under first of A. What is first of A? First of A is small a. So, S to A should be in the row S under terminal A. Now, coming to this, in the row A, column given by first of A, B, A dash, which is nothing but first of small a. So, A to A, B, A dash. Coming to A dash to D, A dash. Where do we place? Row is A dash, column is first of D, A dash, which is nothing but D. Hence, A dash to D, A dash. What about A dash to epsilon? Row is A dash, column is first of epsilon. Whenever first of the right hand side contains epsilon, it should be under follow of A dash. What is follow of A dash? Look at the rule. You have A dash here. Follow of A dash is follow of A dash. Follow of A dash is follow of A. Follow of A is follow of S. And what is follow of S? S is a start symbol, hence dollar. So, A dash to epsilon under dollar. Okay. Now, let us take the next rule. B to BBC. So, row is B, column is first of BBC, hence B to BBC under B. Next, B to F. Row is B, column is F. B to F. And then C to G. Row is C, column is, because it is a terminal, simply row and column is given here itself. This is how we can construct the parsing table. Now if you look at the parsing table, see, to check out the number of entries should be each of this production should be there. Okay, so look at this 1, 2, 3, 4, 5, 6, 7. So each and every rule is there. You need to sometimes at multiple places also same production may come. So you need to check out whether you have considered every rule or not. Every rule is considered. We have taken care of every rule, finding the position of each rule in the parsing table. Now after constructing the parsing table, the traditional procedure of checking whether the grammar is ll1 or not is what? In the parsing table, if you find one multiple entry also, we may say it is not ll1. No multiple entries clearly indicates grammar is ll1. Look at this. We don't have any multiple entries anywhere. Okay. You don't have any multiple entries. Everything is a single entry only. Hence, it is ll1. So, got the traditional procedure. So, what is the problem with this traditional procedure? What exactly we mean by a grammar is ll1? A grammar is ll1 clearly indicates that this grammar is suitable for parsing table construction. So, before applying the tedious procedure, first you need to know whether it is suitable or not. But assume that if a grammar has some 1000 productions or 1000 non-terminals, then how do you verify whether it is suitable for ll1 parser construction? Do you have to prepare a table with 1000 rows and whatever may be the columns, number of terminals, 1000 terminals or 1000 non-terminals for example, 1000 by 1000? And at the end, if there are multiple entries, what will happen? You may have to repent, it is not suitable. Is it what we have to do? Let us check out. Do we have to go with the tedious procedure or can we simplify this procedure to check out how a grammar is suitable or not? That is, how to check whether a grammar is ll1 or not. Now, let us see how to verify whether the given grammar is ll1 or not. How to simplify this procedure instead of constructing that parsing table and all. Let's see how do we simplify this procedure. Remember the basic rule what we use in verifying whether the grammar is ll1 or not is, in the construction of the table, once you construct, if there are multiple entries, it is not ll1. So same strategy is used but in a simple manner. Which way we use? So now instead of constructing the complete table, let us focus more on how to verify possibility of multiple entries in the table. When do we get multiple entries in the table? For example, if the given grammar is epsilon free, there are no null productions, let us assume. You have rules like A2, alpha 1, alpha 2, alpha 3 and so on. No doubt all the three rules are to be placed in the same row A. Now if you look at the possibility of multiple entries, what happens here? A2 alpha 1 has to be placed in first of alpha 1. A2 alpha 2 has to be placed in first of alpha 2 in the same row A, and alpha 3 should be placed in first of alpha 3. Suppose if I assume the terminals to be A, B, C, D and dollar. If first of alpha 1 is something like AB, first of alpha 2 is something like BC and this is CD. Then what happens? Whenever there is a common symbol, naturally there will be multiple entries. So because of this, A2 alpha 1 is placed under A as well as B, whereas alpha 2 is B and C. Coming to alpha 3, it is under D and C and D. So A2 alpha 3, A2 alpha 3. So look at this, here you have a multiple entry and here you have a multiple entry, because between these two this is the common and between these two this is the common. So if you don't want to have any multiple entries, what is the condition? If they do not have anything in common, naturally we may not get any multiple entry. So, to check out whether there are no multiple entries in the row A, what should be the condition? First of alpha 1, first of alpha 2, or we will say pairwise, let us take. When there are n also, best part is take pairwise and verify. If they do not have anything in common, or in general we can say first of alpha 1 intersection first of alpha 2 is 5. Nothing is common, pairwise mutually disjoint. Then we say there are no possibility of multiple entries in that particular row. Okay, remember this holds good for grammar rules where there is no null rules. Okay, so this can be stated like this. A grammar without null rules is ll1 if for each production of the form a2 alpha 1 alpha 2 and so on alpha n, what we should do? First of alpha 1, first of alpha 2, all this should be pairwise mutually disjoint, or in general first of alpha I intersection first of alpha j should be 5 for each I not equals to j. Okay, this rule holds good for a grammar without null rules. If there are null rules, what happens? What do we use? If there are null rules, like you have a production of the form a to alpha or epsilon, we place a to alpha under first of alpha, a to epsilon under follow of a. So, in order to ensure that there is no multiple entries in the row A, the condition should be here first of alpha 1 intersection follow of A should be mutually disjoint. There should not be any terminals in common between these two. Then we can ensure. So, whatever may be the grammar, how many rules it may have, depending on whether it is a null production or non-null production, just these two powerful rules would be sufficient to check out whether it is ll1 or not, because each of these rule tells you whether there is a possibility of multiple entries in the table. So, let us generalize this. A grammar with null rules is ll1 if for each production of the form a to alpha or epsilon, this should be empty. So, equal to 5 indicates there is no symbol in common. When there is no symbol in common, this is ll1. If this is not satisfied, it is not ll1. Okay. And not only this, remember a left recursive grammar also cannot be ll1. For example, when you have something like e2 e plus t or t, what happens if you apply? Remember, these two rules are sufficient, okay, which can be even used for verifying this also. A left recursive grammar, when you take, is it ll1? We have now discussed the two powerful rules. Let's apply the rules and check out what happens. So, if this is not ll1, what should happen? First of e plus t and first of t should be empty set. What is first of e plus t? It is first of e. First of e will be always dependent on even first of t. Hence, this can never be an empty set. So, if it is if it is containing something in common, because automatically it will have even this also. So, naturally it will have input strings derived from the other alternative. So, it can never be a empty set. That's why we say left recursive grammar cannot be ll1. So, here you may get a doubt. Eliminate the left recursion. Remember, left recursive grammar can never be ll1. Though this is not suitable, a left recursive grammar is not suitable for ll1 parser construction, because out of all the parsers, ll1 parser is little simple. If you really want to go with only ll1, the solution is eliminate the left recursion and then construct the table. But as it is, if you consider left recursive grammar, it cannot be ll1. You get multiple entries in the table. Okay. So, but just by looking at the left recursion, you can even say that it is not ll1. Similarly, ambiguous grammar. When you consider any ambiguous grammar also cannot be ll1. Let us take an example. Apply the rules. So if this is not ll1, what should be the condition? First of A and first of second alternative, that is A. If you take the intersection, this should be empty set. But what happens here? What is first of A? First of A is A and first of small a is also A. So this is not empty. Hence, it is not ll1. Remember, if the grammar is ambiguous, naturally you get multiple entries in the parsing table. So, when you know pretty well that the given grammar is ambiguous, immediately you can conclude that it is not ll1. Suppose given a grammar, if you are not able to identify the ambiguity, need not have to worry. Remember, these two are the most powerful rules. Simply apply these two, then automatically these conditions will be violated if it is left recursive or even if it is ambiguous. So just remember these two. If a grammar is without null rules, pairwise first of all alpha 1, alpha 2 should be empty set. If it is with null rules, first of alpha and follow of A should not have anything in common, mutually disjoint. Okay. So just by using these rules, we can check out easily whether a given grammar is ll1 or not. Okay. Let's understand this by taking few more examples. Let's check whether these grammars are ll1 or not. Let's take the first example. So how do we check this? Do we have to check the first rule here? No, since it is only one rule defined here, no need to check out. When there is only one rule for a non-terminal, no need to check out. We can be very confident that there are not going to be any multiple entries in that particular row. Coming to the second one, apply the rule. First intersection epsilon means follow of A should be 5. Is this satisfied here? Yes, this is C. But whereas follow of A is what? Follow of A is first of BB. What is first of BB? First of BB is D here. Otherwise, let us write here. Follow of A is first of BB. First of BB is D. Now, because of epsilon, it goes with B. So, look at this. Here it is C, whereas here it is DB. That means condition is satisfied. That shows, see, when the condition is satisfied, what does it mean? In the row A, there is no multiple entries. Okay. Now, coming to this, how do we verify? First of first alternative is D, follow of B. What is follow of B? This should be 5, isn't it? Follow of B is what? P. So, here it is D and whereas this is B, condition is satisfied. So, we have verified in each row. After verifying in each row, now we can confidently say that this is ll1. Now, the grammar is ll1. So, row wise we are verifying. Actually, here if you notice, suppose if there are multiple entries also, by using the same rule we can check out where exactly the multiple entries are occurring. Okay. Anyway, in this example there is no multiple entries. Let's look at the second example. Only one rule, so no need of verifying anything here. Here also one rule, no need of verifying anything. Coming to row A, in the row A, first of first alternative is A and next we need to check out follow of A. What is follow of A? Follow of A is, so if it is ll1, this condition should be satisfied. So if you look at follow of A is first of B. Okay. What is first of B? First of B is B. Now because of epsilon, it is even follow of A, which is $. So look at this. Here you have A, whereas in the other rule it is B $, nothing in common. Hence the condition is satisfied. That means no multiple entries in the row A. Similarly, if you take the second one, row B. So first of first alternative is B, follow of B. What is follow of B? Here we have seen fall of B is fall of S, and I am sorry, here fall of S is actually hash, not dollar. Fall of S dash is actually dollar. Here start symbol is S dash, not S. Okay. So fall of B is fall of S is hash. Nothing in common, rule is satisfied. So no danger. Now we can say this is ll1. Second grammar is also ll1. This is also ll1. Similarly, let us verify the third one. Take the first rule. First of first alternative is A because starting with a terminal, and follow of yes. This should be fine. What is follow of yes? Follow of S is dollar. So A and dollar, nothing in common. Condition is satisfied, so no danger in the row S. Coming to the second one. Follow of first of first alternative is B and follow of B. What is follow of B? Let us write straight away. Follow of B is follow of S, which is dollar. So condition is satisfied even in the second row. Coming to the third row. First of first alternative is C. Follow of C. Follow of C is follow of B. Follow of B is follow of S. Hence it is dollar. Condition is satisfied here. No danger. Hence this is also ll1. So row wise possibility of multiple entries can be checked out by using those two rules. Let's have few more examples. Let's look at these examples. Let us check out whether it is ll1 or not. Take the first example. There is only one rule here, no need to verify anything. Coming to the second one, first of first alternative is A, then follow of S. What is follow of S? Follow of S is hash here. Follow of S is follow of A. Okay. Here also you have S. Look at this. Here also there is S. So follow of S is follow of A. Follow of A is first of A, hence also A. Condition is violated here because A is common between the two. So when you could find that there is a multiple entry in the row S, no need to continue with the next rule. Just by looking at this, even if there is a multiple entry at one place, immediately we can say that the grammar is not ll1. So this grammar is not ll1. So here in this particular question, if it is asked like check whether it is ll1, by verifying this you can say, or if the question is asked like where do you find multiple entries in ll1 parsing table, means for that also you can follow the same procedure. For example, here when we have applied the rule, where actually what is the common symbol here? It is A. Which row? Yes. So in the row yes, under the symbol common symbol A, we find the multiple entries AAA and S2 epsilon. So the same procedure you can use even for finding the multiple entries. So here the question can be, where do you find multiple entries in the parsing table? Wherever this rule is violated, that is where you find the multiple entries. Okay, you can use the same procedure this way. Let us check out with the second example. So this is not ll1. Let's take this a grammar. No need to verify in the first row. Now coming to the second row, it is first of BB. What is first of BB? First of B is A. Now because of epsilon, it continues with the next symbol, hence it is B. Now coming to the other alternative, it is first of CD. What is first of C? First of C is C here. Now because of epsilon, it continues with the next symbol, that is D. Do you find anything common here? No. So rule is satisfied. No multiple entries in the row A. Coming to second row, what is first of first alternative? A. Epsilon means follow of B. What is follow of B? It is B. So rule is satisfied. Now coming to the last row, first of first alternative is C. Epsilon means follow of C. So what is follow of C? Follow of C is follow of C. Here follow of C is first of D, which is D. Hence rule is satisfied. Since rule is satisfied in each row, we say this is ll1. Let us take this example. What is first of first alternative? First of AA. What is first of AA? First of A. First of A is A comma B. Now if you look at the second alternative, it is B. So here itself we have a common symbol. We need not have to check for the other, because if the question is check whether it is ll1 means here itself you can conclude that by seeing a common symbol between the two, we say it is not ll1. But let us check out even the other one also, or let us change the question like this. Find out the possible entries in the multiple entries in the parsing table. What about here? Here it is C and the last one is D. So, rule is not satisfied. You have multiple entries in the row S under B, because the common symbol is B. Under B, what are the multiple entries? S2AA is placed under B, also S2B also placed under the same rule. These are the multiple entries in the table. Coming to this, first of first alternative is A, first of second alternative is B. So, no multiple entries. Coming to row B, first of first alternative is C, first of second alternative is D. That means no danger. The only multiple entry in the parsing table is in the row S under the column B. You have two multiple entries. Okay. So, we have discussed about ll1 parsing table and ll1 grammar checking. Remember, out of all the top-down parsers, the most widely used parser is ll1 parser only. Though ll1 parser is most widely used and the procedure is very simple, the disadvantages or restrictions in the ll1 parser is it can parse only small class of grammars. All the grammars cannot be parsed by ll1. Best example is recursive grammar. You take recursive grammar, which is actually is not an ambiguous grammar, isn't it? Though it is not ambiguous, such grammars cannot be parsed by ll1 parser. And other thing is, in order to construct any ll1 parser, remember there is a restriction. What is the restriction? Grammar should be free of left recursion and should be left factored. Though the process of eliminating the left recursion and left factoring is easy, remember after doing that the resulting grammar becomes little difficult. It loses its readability. That's why ll1 parsers are also once again of restricted use. It can be used only to parse only small class of grammars. Now before going to the next topic, let us look at some previous gate questions on this ll1 parsers. Look at these questions. This was asked in 2005. The grammar A to AA or within parenthesis A or epsilon is not suitable for predictive parsing because the grammar is ambiguous, left recursive, right recursive or operator grammar. So, look at this. When you look at AA, it can be left recursive or it can be right recursive, isn't it? So, when a grammar is both left recursive, right recursive, it is ambiguous. Most suitable here is, no doubt left recursive grammars are also not ll1, but here when you say left recursive, it is even right recursive also. So, left recursive is not the right choice here, ambiguity is the right choice. Okay. Operator grammar we will see later, it is nothing but whenever the grammar does not contain any epsilon or two adjacent non-terminals, then it is called operator grammar. Anyway, that is also failed here because epsilon is there, two adjacent non-terminals are also there. So, answer here is A. Now, look at the next one. This was asked in 2006. You are given a grammar and you are asked to find out the entries in the parsing table. So, M is a parsing table, one is on row S and column is ID, another is row R and column is $. So, how do we find S on ID? So, just build the row S. What are the terminals you have here? Star, ID and $. Where do you place S to FR? First of FR, what is first of FR? ID. So, S to FR would be under ID. That's it. So, S to ID is S to FR. And coming to R dollar, he has asked us even to find out what is here S on ID, next is R on dollar. So for that, look at the rule. R on star S, do you find under dollar? It is starting with a terminal, so naturally it will be R and a star. So other possibility would be R and epsilon. When R derives to epsilon, if you take, it should be placed in the row R, column given by follow of R. What is follow of R? Follow of R is follow of S, follow of S is dollar. So under the dollar we find R epsilon. So here it is R epsilon. That's how you can find a particular entry in the table also. Now coming to the next question. The question here is like, find the multiple entry. Where do you find the multiple entries in the parsing table for this grammar? Let's check out. By applying the two rules, we can once again check out. So look at the first one. Do you find any multiple entries here? This starts with the terminal I, this starts with the terminal A. So this will be placed in column I, this is placed in A, no multiple entries. Coming to the next one, let us look at S dash. S dash, there is a possibility. Here also there is one entry, so one rule, so no multiple entries. Possibility of multiple entries could be there only in the row S dash. So let us build row S dash. Where do you place S dash to ES? It should be under the column ES, because E is a terminal here. Coming to S dash to epsilon, where do we place? Follow of S dash. What is follow of S dash? Follow of S dash is follow of S. What is follow of S? No doubt follow of S would be, since S happens to be a terminal dollar, in addition to this, look at here, here also you have S. So since there are symbols next to S, follow of S would be first of S dash. What is first of S dash? It is even E. So under E and dollar you will find S dash to epsilon. So look at this, multiple entries you get under, in the row S dash under E, the two multiple entries would be S dash to ES as well as S dash to epsilon. So this is how you can even get the multiple entries in the table. Okay, let's look at this example. This was asked in 1998. Build an ll1 parsing table. So given a grammar, generally people may do mistakes in finding the terminals and non-terminals. How do you actually distinguish between terminals and non-terminals? Is it by looking at lowercase or uppercase? No, that's a blunder. We need to consider all the symbols on the left hand side of the production as a non-terminals. For example, here program XY. Other than this program XY, whatever you have on the right hand side are considered to be terminals. So let us just underline terminals here. This is a terminal, this is a terminal, this is a terminal, this is X is a non-terminal, and this is a terminal, this is a terminal, and here S is also a terminal, yes, and let's give some space to distinguish between the two, and this is a terminal, this is a terminal, that's it. Okay. So how many rows in the parsing table? 3 non-terminals, so 3 rows. Program X and Y. What are the terminals you have? Begin, D, semi, and S, end, and dollar. Okay. Now remember, in the parsing table you will never get epsilon because epsilon is not an input symbol. Okay. You never get a column for epsilon in the parsing table since it is not a terminal symbol here. Now let's take every rule and place it in the appropriate place. Since the productions are too lengthy, let's name the productions like this. This as 1, this as 2, this as 3, this as 4, and this as 5. So where do we place the rule 1? In the row program, column is first of the first terminal, that is begin. Now coming to the second one, row X, column is D. X on D is rule 2. Coming to X derives to Sy, row is X, column is, everything is starting with a terminal, so yes. Coming to the fourth rule, row is Y, column is semi. Fourth rule. And coming to the fifth rule, you need to use follow set. Row is Y, column is follow of Y. What is follow of Y? Follow of Y here is follow of Y. Follow of Y is follow of X. What is follow of X? It is end here. So Y on end is 5. This is the parsing table for the given grammar. Remember, in a grammar, if every alternative starts with a terminal, then such grammar is called simple ll1 grammar or S grammar. If it starts with something like A alpha 1, B alpha 2, every alternative is starting with a terminal. It is even called simple ll1 or S grammar. Okay. This was asked in 2001. Question is for compute first and follow sets and construct the ll1 parsing table. Let us have the first and follow sets. What is first of A? First of E, A and left parenthesis, and first of A plus star epsilon. What about follow? Follow of E is what? Follow of E is a start symbol, so dollar. Next to this, right parenthesis. Here follow of E is follow of A, follow of A is follow of E, and here also you have, it is nothing but dollar. Coming to follow of A, follow of A is follow of E, hence dollar and right parenthesis. You have A only here, so follow of A is follow of E. Now coming to the parsing table construction, 2 rows E and A, terminals are A plus star, left parenthesis, right parenthesis and dollar. Where do you place E to AA? Row is E, column is AA. Similarly, E2 within parenthesis E, row is E, column is left parenthesis. Similarly, A2 plus E, A2 star E. Coming to A2 epsilon should be under follow of A. Follow of A is what? Dollar and right parenthesis, and this is the ll1 table. So that's all regarding the non-predictive recursive descent parser, that is ll1